Hello students, this is Dr. Sivanagaraju from IARE. Today we are going to discuss quantization error and DPCM. DPCM means differential pulse code modulation. So in the last sessions, we discussed how to convert an analog signal into digital one. So those operations is elaborately discussed in PCM. So in the PCM, we're having three important blocks. They are sampler, quantizer and encoder. So sampler, which is going to convert the continuous time domain into discrete time domain, whereas the quantizer, which converts continuous amplitude into discrete amplitude. So when the conversion is going on, we're having an error is occurred. That error is called as quantization error. So we are going to discuss what is a quantization error and how to deduce the quantization error and what are the drawback of PCM that is going to overcome in differential pulse code modulation. So these two topics we are going to discuss in this session. Okay. So before going to the topic, here we are going to discuss this topic which outcome and what that course outcome is going to explain about this course. So actually this course is analog and digital communications. So this course having 6 outcomes. So out of 6 outcomes, we are in third outcome. So the third outcome, which explains, illustrates the concept of pulse modulation schemes, demodulation, sampling, quantization, and coding of obtaining of digital data. So here our aim is to convert a continuous signal into digital one. So we are applying those operations, sampling, quantizing and coding. So this here we're going to discuss. So in our topic we're having quantization noise. Okay. So the use of quantization introduces an error defined as the difference between the input signal M and the output signal V. This error is called quantization noise. So why this noise is arising? Here we're having representation levels. Those representation levels are predetermined. So we are going to round off to the nearest value of that predetermined voltage levels. So actual value we are going to round off to the nearest value. So we have some difference. That difference is called as an error. This error is producing the noise. We can call it as a quantization noise. So here Q is the quantization noise and M is the input signal. That means here M is the continuous signal. We are converting this continuous amplitude signal into discrete amplitude signal. So that's why here M minus V. So when a conversion process, in the conversion process, we're having this error. That error is called as quantization error or quantization noise. So there is no difference between error and noise. Okay. So here you can see that this is our input signal, the dashed wave, and the staircase we are having seen that is a quantized output. So the difference you can show here below, that error, that is the difference to the actual value to the round off value. We are getting that quantization noise. Now we are going to derive this quantization noise. Why? Because many of problems we are going to solve by using this formula. So we are going to derive this quantization noise. So first we are considering a continuous amplitude signal in the range of minus mmax to plus mmax. So here we are assuming a uniform quantizer, and again in the uniform quantizer we are having two varieties. One is mid-rise and mid-trade. So here I am using mid-rise type, not a mid-trade. So, and again we know that the step size. The step size is nothing but the separation between the represent levels or quantization levels. Why? Because our quantizer having this type of arrangement. So these are the levels, quantization levels or representation levels. So here this is my delta. This delta means the separation between these levels, predetermined representation levels or quantization levels, whatever it may be. So here the step size is given by 2 mx by L. Why? Here having the range minus mx to plus mx. So the total value is 2 mx divided by number of L, number of levels. Number of levels is L. What is L? Where L is the total number of representation levels. Okay. So for a uniform quantizer, the quantization error Q will have its sample values bounded by. So this is the region where this quantization error is introduced. So minus delta by 2. So what is delta? So delta is the spacing between two reference levels. So here it depends on the levels. Why? Already we mentioned delta is equal to 2m max by L. So where I got this delta? From the maximum amplitude of the input signal and how many levels used in the quantizer. So where this error will be introduced. So this is the region minus delta by 2 to plus delta by 2. And here we may express the quantization error as a probability density function. So FQ of Q is the probability density function of quantization error, which is equal to 1 by delta. So this is the region where this error is available, minus delta by 2 plus delta by 2. Otherwise, this density function is 0. Okay. So here we are taking the variance. Why? The mean of the quantization error being 0. So here I am taking the variance. So variance is nothing but the same as the mean square value. So here I am using this probability density function. So it is a value of integral minus delta by 2 plus delta by 2. So sorry, minus delta by 2 plus delta by 2. Q square FQ of Q dq. So FQ of Q is nothing but a probability density function of this quantization error and is nothing but mean square error. So mean square value and the variance, both are the same. So here I am going to substituting this probability density function in the variance. So we are having integral minus delta by 2 plus delta by 2 q square fq of q dq. Actually fq of q is 1 by delta. So here we are going to integrate this q square, which is nothing but q cube by 3. The values are minus delta by 2 plus delta by 2. So 1 by 3 delta, having delta by 2 whole cube minus delta minus of delta whole cube by this 2. So totally having 1 by 3 delta cube by 8. So minus of minus plus delta cube by 8. So totally having 1 by 3 delta into 2 delta cube by 8. So here this delta is going to cancel delta square terms, and this 2 by 4 to finally having delta square by 12. So this is the variance of this quantization noise value. Okay, and next let R denote the number of bits per sample used in the construction of the binary code. So why? Because here we know that the procedure how to convert an analog signal into digital. It is nothing but ADC, analog digital conversion. Sampler, quantizer and encoding. So after quantizing we are having encoding. So here my encoder, how many bits is going to encode? So this R denotes the number of bits per sample in the binary code. So it may be denoted as N or R. So it may value is 3. Here you go to substitute L value is 2 cube is nothing but 8. So depends on the number of bits my quantizer having that levels. This L is used in quantizer. So this L is depends on how many bits is going to encode in the encoder. So L equal to 8. So that means I required 8 levels. For how many bits to convert? 3 bits. For 3-bit conversion, I use 8 levels. So again you can take in the value of R is equal to log 2L. Okay. Now I am going to substitute the L value in the quantizer step size. Why? Already you know that delta is equal to 2m max by L. So what is here L? 2 power R. So I am going to substitute this L value. So I got delta is equal to 2m max by 2 to the power of R. So what we are doing here? We are going to convert. We are finding the value of quantization to noise ratio, SNR, signal to quantization noise ratio, signal to noise ratio. So here we are going to calculate for this SNR of this receiver. Okay. So the average power of quantization noise is sigma square. What is sigma? Here it is a variance or mean square value. So sigma square Q, which is equal to 1 by 3 m square max to the power of minus 2r. Why? Here already we know the value. It is nothing but delta square by 12 we got. So here the average power we taken as 1 by 3 m square max to the power of minus 2r. Already know what is R. R is nothing but number of bits to encode in a sample. M max is the maximum value of the analog signal. So let P denote the average power of the message signal, M of t. We may then express the output signal to noise ratio of a uniform quantizer as a SNR output is equal to P by sigma square Q. So we are going to find this output signal to noise ratio of a quantizer. So why? Because we are doing all this here. We know that sampler, after sampler we are having a quantizer, then we are having encoder. So here we are going to calculating this SNR for this quantizer. So when you are going to convert analog signal into digital, we are having that error. That error is called as quantization error or quantization noise. So by considering that noise, how much signal to noise ratio we are having. Okay. So SNR output, which is equal to 3P by m square mx into 2 to the power of 2r. Why? SNR is nothing but signal to noise ratio. So P is the average power of the input signal or analog signal, and already you know that sigma square Q, that is variance of the quantization noise. I am going to substitute all this. So the output signal to noise ratio of the quantizer increases exponentially with increasing number of bits per sample node. Why? Here, when the bits is increased, or my value of SNR is going to increase. Okay. So this is the quantization noise signal to ratio. So here we're going to one problem regarding this quantization noise. Okay. So in this problem, given in a binary PCM system, the output signal to quantizing noise ratio is to be held a minimum of 40 dB. Determine the number of required levels and find the corresponding output signal to quantizing ratio. So here we are considering PCM system. Why? Already we covered PCM system, pulse code modulation system. So the output signal to noise ratio they given, it is 40 dB. By using this SNR output, we are going to find how many levels. The levels means representation levels are quantization levels, and find the corresponding output signal to quantizing ratio. So for this we use a formula that is nothing but S by N2 dB, which is equal to 1.76 plus 20 log of to the power of R. So here we can use direct L or in terms of bits. Okay. So here we return again it as 1.76 plus, here it comes into R. So 20 log base 10 to, we can get 6.02 into R. So this is my signal to quantizing ratio in dBs. Signal to quantizing noise ratio in dBs. The value is equal to 1.76 plus 6.02 R. So what actually they given, its value is 40 dB. Here in the left hand side we are having signal to quantization noise ratio in dBs given as 40. So here I am going to convert this 40 dB into value. So S by N2 naught is equal to, so it is in dBs, is equal to 40 dB. So this is the given. So when you convert into value, so S by N2 output is nothing but 10 1000. So here SNR output is equal to S by NQ output, which is equal to 3 by 2 L square. So this 3 by 2 L square, which is equivalent to the above equation 1.276 plus 20 log to the power of R. Okay. Why? Because it's nothing but 2 power R is L. Okay. So both are the same equations. So here I am going to find L. Why? Here they ask determine the number of required levels. That level is nothing but L. So L is equal to, so here L I require in the right hand side. So I convert, I send this 3 by 2 to the left hand side. So it's nothing but 2 by 3 into, here what is my S by NQ naught value? 10,000. 10,000. And here square is there. So it moves on the other side. It's converted as square root. So when you're using calci, you can find this value as 81.6 nearly. So approximately I am going to round off to 82. So here the L value is 82. That means 82 are the required levels. Okay. So here I am going to find a number of bits, that is R. R is nothing but log 2L. So what is here L? 82. So log 82 base 2. So nowadays the calculus are advanced scientific calculus are available. So we can easily find this base value change. This value R value gets is approximately 6.62. So here I would round off to 7. So here I'm going to find the corresponding output signal to quantizing ratio. So here I got the 7. I can directly substitute in the first equation. So this is my first equation. So equation 1. Here I am going to substitute this R value in the above equation. That is 1.76 plus 6.02 into R. So after substitution of this value, we got this S by NQ output in dBs, which is here 1.76 plus 6.02 into 7. So finally I got 43.9 dB. So this is the value of this given problem. So in this way we're having one number of problems, depends on this formula. Okay, so I think understand. Now we are going to move to DPCM, differential pulse code modulation. So before going to differential PCM, once again we're going to remember PCM. In PCM, here I having information source which produces the required signal, analog signal. I'm going to convert that analog signal into digital one by using 3 operations already we know: sampling, quantizing, encoding. So here in PCM, all the bits is going to encode whatever the signal, whatever the source, information source produces, that information all is going to encoding in PCM. So when you're using all the information into bits or coding, we're having the overall bit rate is going to increase. So this overall bit rate increases, what happens? It affects the bandwidth. So here we have an idea. When you're going to reduce the redundancy, that means redundancy means not essential bits. Some bits having the same information. Why need to encode those bits? Those bits carrying same information. Why need we are going to encode such bits? We are going to reduce that not essential bits. That means we can call it as redundancy. If the redundancy is reduced, then the overall bitrate will decrease and the number of bits required to transmit one sample will also reduce. Why? Because in effective communication, the bandwidth utilization is very, very important. So I'm going to utilize effectively the bandwidth. Then that communication is excellent. The quality is improved. Okay. So I'm going to reduce that not essential bits. Okay. So such type of digital pulse modulation technique is called as differential pulse code modulation. Here I am going to reduce the redundancy. Then the overall bitrate will decrease. So my aim is to decrease that overall bitrate. Okay. So the adjacent samples of the signal carry the same information with a small difference, and sometimes no difference also. So at that time I'm going to reduce that samples. Okay. So the signal's value from present sample to the next sample does not differ by a large amount. Then we can reduce that not essential bits. So the not essential we can call as redundancy. Okay. So how I'm going to reduce the redundancy? When I know the past behavior at some instant, then I can predict its future. Then I'm going to reduce that information. Okay. So here you can say the samples 40 years, 5 years, 6 years having the same information. So here these three having the same information. Why need to transmit these three? Whereas in PCM, these 3 bits are going to encode. So it having increases the bitrate, then corresponding it utilizes more bandwidth. So here I am going to reduce this redundant information in differential PCM. Okay. So for this I am using a transmitter, that is a DPCM transmitter. I having the sample, that means a sampler is nothing but sampler, quantizer, encoder. So these 3 are same as in PCM. But what is the new here? Here the new one is the prediction filter. Here I am going to predict which value is same. I am going to reduce that redundant information. Here you can be used x of t as the input signal, that is a continuous signal or message signal. So here you can use x of t or m of t, both are same. So after sampler it is considered as a discrete. So x of nts and here I'm giving this x of NTS to the comparator. So the comparator having another input as x cap of NTS. This one is the predicted value. So here I'm going to compare to this sample value to the predicted value. Here I got E of NTS, that is error. So E of NTS you can write as M of NTS minus M cap of NTS. And this M of NTS, which is given to the quantizer. So the quantizer which converts as EQ of NTS, and this is given to the protection filter. Finally it is given as the protection filter. The protection filter is nothing but a tap delay line filter. After quantizer, we are given to the encoder. So the encoder produces this DPCM signal. Okay. So here the first three operations, what is a sampler, quantizer, encoder, is similar or same as the PCM transmitter, but here the new arrangement is taken as the protection filter. So the protection filter is nothing but a tap delay line filter. It having some weights. So we are giving this sampled signal, that error signal. Here what are given? EQ of NTS as one input to the summer, and again another input as the predicted. So this predicted input value and quantized input value is summing, and finally produce this XQ of NTS, or we can call it as MQ of NTS. So this value is given to the protection filter. Then the protection filter produces this predicted value M cap of NTS or X cap of NTS, whatever we can call it. Okay. So here it goes to the feedback. Look. So finally, whenever this error is reduced, error reduced means here the predicted value as same as this X cap of NTS, and this one value is going to quantize. That value is encoded into bits. Okay. So here we can see MQ of NTS, the quantized input is given to the tap delay filter. So W1, W2 up to WP is weight, prediction weights, and those all weights and the delay inputs are going to summarize. Then we get M cap of NTS, that is my predicted value. Okay. Now the sampled signal is generated by X of NTS. The predicted value is generated as S cap of NTS, and the signal error is E of NTS. So already we discussed this E of NTS is nothing but X of NTS minus S cap of NTS. So here we are having the comparator. So for this comparator we are giving this value. This is X of NTS, and another one is X cap of NTS, and the produced one is E of NTS. So this we can take it as equation 1. And next the quantized error signal EQ of NTS is very small and can be encoded by using a small number of bits. So the quantizer output would be written as EQ of NTS is equal to E of NTS plus Q of NTS. So here Q of NTS is again quantization error. Why? Because we are using quantizer. So whenever you're using the quantization error will always produce. And E of NTS is the required one. So this E of NTS is error signal, what you see in the equation 1. So from the block diagram, the protection filter input X2 of NTS is obtained by sum of X cap of NTS and the quantizer output EQ of NTS. So we can written as equation 3, that is X2 of NTS is equal to X cap of NTS plus EQ of NTS. So this is the protection filter input. By using this protection filter input, the filter which is going to produce the protected value. So by substituting the value of EQ of NTS from the equation 2 in equation 3, we get XQ of NTS is equal to X cap of NTS plus U of NTS plus Q of NTS. So we are taken as equation 4. And again equation 1 can be written as U of NTS plus X cap and X cap of NTS is equal to X of NTS. So from the above equations 4 and 5, we get XQ of NTS is equal to X of NTS plus Q of NTS. Is nothing but here in X of NTS is M of NTS or message signal. The sample version of the message signal plus this quantization noise is coming. So therefore the quantized version of sample XQ of NTS is the sum of original sample value and quantized error Q of NTS. So that is transmitter. Now we are in the differential PCM receiver. So this is a DPCM receiver. So here also same, we are using same filter with the same weights what we use in the transmitter. So the DPCM input as taken as the input to the receiver. So here initially we are having a decoder, while at the end of the transmitter is encoder. So here the starting stage is a decoder. So after decoder we are getting that decoded value. So the decoded value is again given to the summer and it is come to the protection filter. So finally we are getting the reconstructed signal as the output. So in the absence of channel noise, so find that encoded signal at the receiver input is identical to the encoded signal at the transmitter output. So channel noise. Why? Because whenever signal enters into channel, the channel noise will add up. So generally noise is additive property, so it always added. So accordingly the corresponding receiver output equal to X2 of NTS, which differs from the original input X of NTS by the only by the quantization error Q of NTS. When you are using the quantization, you got this quantization error and include as a result of quantizing the prediction error E of NTS. Why? Because in the transmitter we are having this prediction error E of NTS. So E of NTS is nothing but X of NTS minus X cap of NTS. X cap of NTS. So this is my E of NTS. So here we are going to find this prediction error. This prediction error is going to apply to the quantizer. We get the quantized output. Thereafter, we are going to encode. Okay. So references here. This total content of information is taken from Communications by Simon Hacking for edition. Okay. So I hope to that understand this differential PCM. So the main drawback of the PCM system is it is going to encode whatever the bits is coming totally. So the data rate is going to increase. So once again you can see that transmitter of this DPCM transmitter. So actually in a PCM we're having this type of arrangement. This is a source and this one is sampler and this is quantizer and this is my encoder. So This is the actual arrangement of PCM. So here, whatever the source sending the information to sampler, the total information is going to encode. So all bits are going to encode. So that's why here this drawback of PCM transmitter is bitrate is going to increase. Bitrate is increased, or data rate is going to increase in PCM. So when data rate is going to increase, the transmission bandwidth utilization is also going to increase. So here we are going to reducing, our aim is to reduce this data rate and transmission bandwidth by using this protection filter. The protection filter which is going to predict which value is useful. When not useful means our information is going to reduce. So this is the special arrangement of this DPCM transmitter having is nothing but this protection filter. Okay, so this is the main advantage of the DPCM transmitter, differential pulse code transmitter. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.